Welcome to today's Explainer. Okay, so today we're diving into something that, honestly, it completely changes how you look at the physical world around us. A lot of people think geometry is just about rote memorization, cramming formulas and rules until your head spins. But I'm here to excitedly tell you that it is absolutely not. It's actually about understanding the beautiful, logical language of shapes. Because once you know the alphabet, you can read the geometry of the entire universe.
Okay, let's dive into this roadmap. We're going to start with the basics of shapes, then step up to polygons and their specific rules, and uncover the secret of angles. After that, we'll explore the quadrilateral family, and finally wrap it all up with the magic of diagonals.
Section 1. Basics of shapes. So let's kick things off with the absolute ground floor of geometry. Imagine you place your pen down on a totally flat surface, like a piece of paper, what we call the plane, and you just draw a continuous path without lifting your pen. That creates a curve. Now these paths divide into two main flavors. Open curves are kind of like a path with an open gate. You start drawing at one point, wander around and stop somewhere entirely different. The starting and ending points just don't meet. Closed curves, on the other hand, are like a sealed room. You draw your path, and the starting point and ending point perfectly meet. There's literally no open door to get inside.
But we can actually break these down even further. Simple curves are your clean, straightforward paths that never cross over themselves. They're super neat. Non-simple curves are completely tangled up. They intersect and cross over their own lines, making all these little loops and knots. But hey, going forward, we're going to focus our energy on the neat, clean, simple ones.
Section 2. Polygons, types, and rules.
So what happens when we take those simple, closed curves, but we build them using strictly straight-line segments? Well, enter the polygon. Let's clearly anchor this definition before we move on. A polygon is a simple, closed curve made entirely of straight-line segments. No curved edges allowed whatsoever. And the word itself is actually a great cheat code. Poly means many, and gon means sides. So many sides. Triangles, squares, pentagons. Yep, these are all polygons.
Now, we categorize these shapes based on their visual structure. We've got convex and concave polygons. In a convex polygon, all the interior angles are strictly less than 180 degrees. It looks, pushed outward. But a concave polygon has at least one interior angle that's more than 180 degrees. The best way to remember it? Just look at the word concave. It literally has a cave shape pointing inward. It's caved in.
Okay, now look closely at the concept of a regular polygon. This is where we find perfect harmony in geometry. For a polygon to be considered regular, it absolutely must have both all sides of equal length and all interior angles perfectly equal. If even one single angle or side is off, boom, it becomes an irregular polygon. It requires both of those equal conditions to achieve that perfect regular status.
Section 3. The secret of angles.
All right, we have the foundational definitions down. Now let's put on our detective hats and uncover the hidden mathematical laws that govern the inside and outside of all these polygons. There is this brilliant logical formula to find the total sum of the inside angles of any shape. It's just the number of sides, which we call n, minus 2, multiplied by 180. Why? Because every shape is essentially just made up of hidden triangles. A three-sided triangle is 180 degrees. A four-sided shape has two hidden triangles inside it, so that's 2 times 180, which is 360 degrees. A five-sided pentagon has 3, so 540 degrees. See? It's completely logical.
But here is the real aha moment. While those interior angles grow larger and larger as you add more sides, the exterior angles have this incredible, unwavering rule: 360 degrees. Seriously, no matter if your polygon has 4 sides or 400 sides, if you walk around the entire outside boundary of the shape and add up all those exterior turns, it will always sum up to exactly 360 degrees.
At this point, you might be thinking, do I really have to memorize all these rules? Absolutely not. Take a deep breath. By simply grasping the underlying logic, like visualizing those hidden triangles inside a shape, or picturing that continuous 360-degree walk around the outside, there is zero need to blindly memorize. The math is really just a language describing what you can see.
Section 4. The quadrilateral family.
With that empowering thought, let's enter the main event of today's Explainer. We're going to view four-sided shapes, our quadrilaterals, as a giant, fascinating family tree where children inherit distinct traits from their parents. Here are the three main branches of our four-sided family. First, the trapezoid. It's pretty modest. It only has one pair of parallel sides. Then the kite, which has two pairs of adjacent equal sides,
meaning the ones right next to each other are equal, but the opposite sides are not. And finally, the parallelogram. This is the absolute boss shape of our family tree, rocking two pairs of perfectly parallel and equal opposite sides.
Let's look a little closer at the parallelogram's DNA. If you are a parallelogram, your opposite sides are perfectly parallel and equal in length. Your opposite angles across the shape are identical, and your adjacent side-by-side angles always add up to exactly 180 degrees. This genetic foundation is about to get passed down to some very famous children.
First up, the rectangle. The rectangle is a direct child of the parallelogram. It inherits absolutely all of those boss rules we just talked about, but it adds its own special twist. It stands up perfectly straight. It fixed its posture so that every single one of its 4 interior angles is exactly 90 degrees.
Next, we have the rhombus, another child of the parallelogram. It also inherits all the base rules, but instead of fixing its angles like the rectangle did, the rhombus equalizes its borders. It decided to make every single one of its 4 sides the exact same length.
And this all leads to the ultimate descendant, the square. The square is like the perfect grandchild in this family tree. It inherits absolutely everything. It takes the perfectly equal sides from the rhombus, and it takes the perfect 90-degree standing posture from the rectangle. It really represents the absolute pinnacle of quadrilateral evolution.
Section 5. The magic of diagonals.
But wait, the story doesn't end at the perimeter. Let's shift our focus to the hidden, internal bones of these shapes, because this is where the real magic happens inside the family tree. First, let's define our terms. What exactly is a diagonal? It is simply a straight line segment connecting any 2 non-consecutive points of a polygon. Basically, it's a line that jumps straight across the shape's interior space, completely skipping over the immediate neighbor point to connect to one further away.
Notice how these internal bones evolve. In the boss parallelogram, diagonals simply bisect, meaning they neatly cut each other in half. But look at how the children evolved. The rectangle's diagonals became perfectly equal in length. The rhombus's diagonals evolved to intersect at exactly 90 degrees. They each developed completely unique magical properties inside.
And then there's the square. Just like its sides and angles, the square has the absolute most perfect, rule-abiding diagonals of all the shapes. They bisect each other exactly in half, they are perfectly equal in length, and they intersect at a perfect 90-degree right angle. It gets the absolute best of both the rectangle and the rhombus worlds, the whole shebang.
So here is the big takeaway from our explainer today. If you master these basic building blocks, understand the simple lines, the logical rules of angles, and these family traits, you literally unlock the hidden rules of absolutely any complex shape in the universe, all without the stress of rote memorization.
I'm going to leave you with this to ponder. If you can use this simple logical framework to completely decode the DNA of a 4-sided shape, what kind of hidden secrets could you discover about a shape with 100 sides? The rules are exactly the same, just waiting for you to apply them. Keep questioning, keep observing, and you'll see the magic of geometry everywhere.